This is the second part of Lecture 3 on nuclear reactions for RadChem 702. We're going to talk about nuclear reactions in some details. We'll talk about the types of reactions, some of the energies that are required for these reactions to occur, and then we'll, as an example, discuss nucleosynthesis as a combination of these reactions and how elements are made in stars through these nuclear reactions. We're going to start with light projectiles for nuclear reactions, and the first set of nuclear reactions aren't really reactions at all, but really scattering. In elastic scattering, kinetic energy is conserved and particles do not change. Really, this is the simplest type of reaction, scattering, for instance, as an example of an elastic reaction. There's no change in particle identity in the process, and scattering will have a contribution from nuclear forces. So for this reason, elastic scattering can be a way to understand some behaviors of nuclear forces in the target that is scattered, that scatters the projectile. An example of some other low energy reactions with light projectiles is one that we're interested in would be slow neutron reactions, so thermal neutron reactions. This is really the purest example of compound nucleus behavior. There's a rate that governs this, where 1 over the velocity or the energy law governs most neutron reaction cross-sections. So we see that we tend to see a decrease in a cross-section with an increase in the neutron energy. The neutrons that are available for these reactions can only come from nuclear reactions. Therefore, a range of neutron energies can be obtained since these neutrons are being produced in fundamentally the fission of a nucleus. Now, the reaction cross-sections, as we see from the data here, vary. They generally start high, go low, but there's resonance peaks throughout the energy regime that is examined, in this case for the fission of uranium-235 by thermal neutrons. Now, there are some aspects of this that are influenced by the particle. For instance, the reaction cross-sections are going to be influenced by the Coulomb barrier. And the Coulomb barrier prevents charged particle reactions below 1 MeV. And here's an example of what one can see if we evaluate this is for neutron energy. As we increase neutron energy, we go from high to low. Now, charged particles, they go low and basically sub Coulomb barrier. There's no reactions. The reactions increase with the cross-section increases with energy until both parts at very high energies we start to get cross-sections that are on the order of barns, fundamentally based upon the geometric mean. Other low energy reactions with light projectiles include deuterium or deuteron reactions. In these reactions, you can think about that with deuterium, you have 1 proton, 1 neutron in the nucleus. So you can think of almost that the proton is carrying the neutron around. So this is, in essence, you can think of this as a way of accelerating a neutron by exploiting the fact that that neutron is connected up with a proton. And some of these reactions can actually occur where the neutron can get into the nuclear, it can penetrate the nuclear barrier while the proton is still outside most of the Coulomb barrier. And this is due to the fact that there's inherent large neutron-proton distance in deuterium. This weakly bound nucleus, H2, can be broken up. The proton remains outside the barrier. So it's a way of having neutron reactions that can exploit this charge of the proton, so you can fundamentally have these neutron-based reactions in an accelerator. Now, there's a number of competitions amongst reactions, and they're going to really depend upon the probabilities for emissions of the various particles from the compound nucleus. These probabilities are going to be based upon energy available, the Coulomb barrier, and the final states of the product nucleus. if the energy of a light particle is produced, the reactions can change. An example of this is for high energy protons, and you can get something called spallation. Spallation is if you use a high energy product, a light particle such as a proton, you're going to get a number of products that are formed within the immediate neighborhood of the target. Let's say between 10 and 20 mass numbers. An example here is shown for lead, where a proton, high energy proton, this is hundreds of MeV, impinges upon lead, excites the lead nucleus with the emission of neutrons and protons. You'll tend to make beta stable, medium weight products, and this route, spallation products, is used to produce neutrons at spallation neutron sources. Heavy Z's will produce 20 to 30 neutrons per proton interaction, and there's a web page listed here for the spallation neutron source that's run at the Oak Ridge National Laboratory that has information on this technique and the application of it for developing neutron sources. The other reaction that will occur is that you can still induce fission with high energy neutrons, but the distribution of the fission products will change. And as we see here, here's an example of some data for uranium fission by successively higher neutron energies, 30, 45, 60. And what's observed is that the relative fission distribution changes as a function of energy, and this is both shown for experimental and modeling data. The modeling tends to drive it. There's a big difference here at 60 MeV. You get some differences in the distribution, but one of the trends that we do see is that at higher energy we tend to get more symmetric distribution. Particularly here, what's observable is we see a decrease in this low valley number. These high energy reactions, they vary from the low energy reactions by the way the product nucleus behaves. At low energies, you tend to get a compound nucleus. So the products form and they tend to stay together at a nucleus. Now above 100 MeV, you start to get some changes where you get lots of excitation within the nucleus. A lot of the particles start to become, the neutrons and protons can get to higher energy states. Therefore, we can see some differences in behavior, such as these emission of many neutrons. You can imagine that these neutron emissions are fundamentally routes for de-excitation of the excited product nucleus, where each neutron emission is responsible for dissipating between 5 and 10 MeV of energy. So the model for this is a cascade evaporation model. It's listed here, usually above 100 MeV reactions. And the protons will collide with one nucleon at a time within the nucleus. These high energy protons make only few collisions in the nucleus, and they produce nucleons with high energy. Another route of reactions is moving from lighter particles to heavier particles. So as opposed to using a proton, think about bombarding a nucleus with something like oxygen-16. So we have these heavy ion reactions, and these heavy ion reactions, in a lot of ways, they're similar to light ion reactions, where we can have elastic and inelastic scattering, compound nucleus formations, direct interactions, and deeply inelastic reactions. One of the main differences between heavy ion and a light ion like a proton is that the heavy ion during the reaction can donate some of its nuclear matter to the reaction, whereas in a proton it's either all or nothing. These reactions are influenced by the reaction parameter, which is a function of this impact parameter. It's a function of the radius. It's also influenced by the kinetic energy of the projectile, the mass of the target, and the projectile nuclei. The mass and the target projectile nuclei are going to have an influence on the Coulomb barrier. So you can get information about probabilities or behaviors from scattering and Coulomb excitation based upon the radius information, which comes from the mass of the projectile and the mass of the target. With heavy ion reactions, we can have inelastic scattering, and in this case, some of the projectile's kinetic energy is transferred to excitation energy in the target nucleus. So this means that some of the energy can, from the projectile can go into exciting the nucleon states within the target. This can experience Coulomb excitation. So for high charges below the Coulomb barrier, reactions can occur, and these can excite nuclei purely by electromagnetic interactions. So it's possible with some of these heavy ion reactions to observe changes in the nuclei at sub-Coulomb energies. You can also have transfer reactions where part of the projectile is taken up by the target. So if you have a, think again, oxygen 18, you can perhaps just strip or pick up a few neutrons from the projectile to the target. And these can take place when impact parameters are just below those at which interactions that are purely Coulombic occur. Some of the results of this can be measured with angular distributions, show diffraction-like pattern when transferred to a single well-defined state are observed. So you can get information about nuclear states from some of the behavior on these transfer reactions. Deep and elastic reactions occur when more of the nuclear matter is transferred than just these grazing and incident reactions discussed on the previous page. There are some trends with this, is that the total energies of the products strongly correlated with the amount of mass transfer. So increasing mass differences of product and projectile lowers the kinetic energy. So this way, the nuclei that are involved in the reaction from the projectile to the target can be assessed by evaluating the kinetic energy of the products. Now, the complete interaction of the nuclei, the target and projectile, is called the Compound-Nucleus Reaction. These reactions, as you can imagine, are probably the lowest probability with a high mass, relatively high mass projectile. So these cross sections can be relatively small. During these heavy ion interactions, so the heavy ion interaction being shown here, where the nuclei fuse, there's from when this compound nucleus is formed and it's in the excited state, it can de-excite with the emission of neutron evaporation. And this is the reactions that are used in heavy element production, where you get a compound nucleus formed and the emission of neutrons to form the ground state of the heavy element. These heavy ion reactions are needed for reaching the predicted island of stability in the heavy element regime. So Z of 114, N of 184. And you can get an idea of the excitation energy that's necessary when you look at the mass of the target in the projectile, the kinetic energy, and the binding energy of the projectile in the compound nucleus. So these terms can be used to get an idea of the overall excitation energy that's going to be observed in the nucleus from a kinetic energy of a projectile. For the heavy ion reactions, an overview is listed here, same figure that was shown on the previous page, where we can get collisions that are primarily elastic scattering, some distant collisions where you can get Coulomb excitation of the nucleus, and as the particle comes closer to the nucleus, you can get some transfer reactions. These can also lead to deep and elastic collisions. And then finally, where we get the formation of the compound nucleus, where we get fusion of the particle and the projectile. As you can imagine, the cross sections will decrease as you go from reactions where you don't have to have complete interaction with the nucleus. So these cross sections should be higher than these and then larger than the compound nucleus formation. Now, it's also possible to have nuclear reactions using photons. And these reactions between nuclei and low and medium energy photons are dominated by a giant resonance. These excitation functions for the photon absorptions go through a pretty broad maximum, a few MeV wide, is shown here for the reaction of photons on gold 197. This is due to the dipoles that can set up within the nucleus between protons. One thing about the value here is in millibarns. So reactions, photon reactions tend to have on the order of 500 millibarns. And as we see, the reaction here is gamma n, gamma 2n, gamma 3n. We see it goes through a maximum peak for the 2n reaction at around 14 MeV. The resonance peaks, the way this figure behaves, is going to vary pretty regularly with the A of the target. 24 MeV for oxygen-16 and 13 MeV for bismuth. And there are a number, here are just shown gamma N reactions, but there are actually a number of different reactions possible, including protons, neutrons, and alpha reactions. Now, this has been used to also study gamma fission, as what's shown here, where photons can be used to drive a plasma wave, and we have reactions where we see, as listed here, photon-induced fission. This is actually a route where there's been concepts to probe materials looking for uranium or other fissile material by activating the gamma fission reaction and then observing the neutrons that can be emitted. We can use these nuclear reactions to describe what occurs in stars to produce elements. Now, this is driven by the fact that stars have high temperatures and densities to provide enough energy for nuclear reactions to occur. And once the elements are made in stars, they've been dispersed. For instance, you get here on Earth, the stars disperse their elements through nova, supernova. And these nuclear processes that we just discussed are the primary routes in which are the only routes in which primordial elements are produced. And these include the radioactive elements that we see today, the natural radioactive elements, such as the uranium and thorium isotopes. So if we look at the chart of the nuclides, this black line here, those are all the stable isotopes. And when we talk about the nuclear processes, we'll work our way from here, from the Big Bang, all the way up to here to uranium-238, which isn't necessarily stable. But what we're going to see is that we could get all the way up to bismuth, and then somehow we have to make a leap to hit some of these radioactive isotopes. So those are the processes we'll discuss. The timeline, the Big Bang quickly made protons, helium, and then it took a longer time to get to the distribution of these elements and the formation of elemental distributions here on Earth. The Big Bang was on the order of 10 to the 10th years ago, very high temperatures. Upon cooling, forces were introduced, and within a couple of hours, helium and hydrogen, primarily hydrogen, were produced, along with free neutrons. So we can think about the origin of the elements from after the Big Bang, gravitational coalescence of hydrogen and helium into clouds. Once these clouds got dense enough, temperatures can increase to fusion temperatures. And there's a list of reactions that are given here. So protons plus neutrons going to deuterium, helium-3, etc., peaking at helium-4 reactions, where we get a lot of energy from fusion. Now going above helium, we would make lithium or beryllium, but these were relatively short-lived, so they were not stable. And the initial nucleosynthesis lasted on the order of 30 minutes. The free neutrons, they have a half-life on the order of 10 minutes. So after a period of time, free neutrons decayed and were no longer available for reactions. In stars, we know that fusion occurs. And in fact, this figure here demonstrates binding energy as a function of A and shows why fusion can occur. We know that this is our yield from nuclear fusion. This reaction here, the helium burning, or the formation of helium. Helium burning has a few reactions. So we see here, if we fuse 2 heliums, we get beryllium-8. This is a very short-lived isotope and would not build up in stellar processes. Carbon is formed by 3 helium nuclei colliding. This is a 3-bodied problems. It's actually something that theoretically should be, or conceptually should be, rather rare. However, one of the estimations from this, if one looks at the energy, this reaction would be there'd be higher probability of this reaction occurring if there's a nuclear state around 7.4 MeV. This is called the Hoyle state. And if we see here, looking at the excited nucleus of carbon, we see that there's a nuclear state about 7.6 MeV, close to this predicted Hoyle state. And it's a 0+ state, which were some of the conditions so that we could have a rapid transition from the gamma, from this excited state down to this ground state of the carbon-12. This is one of the hypotheses that was tested for the nucleosynthesis of carbon when these energy states of helium, of carbon-12 were measured. That there was a prediction that there would be a state near this Hoyle band, and that observation proved to be correct. Now, from this binding energy curve, we see that we can fuse elements together all the way up to iron and still get energy. Above iron, and what we're going to see is that above iron fusion no longer is an operable route for obtaining energy and producing elements. Once we start producing carbon, we're able to move beyond carbon to heavier elements. So this is an example of a carbon-nitrogen-oxygen cycle, where carbon reacts with particles such as a proton to make nitrogen, which decays to carbon-13, which can then make nitrogen-14. And some examples are given here for nitrogen reactions. We can also have fusion of carbon, oxygen, to produce heavier elements, along with productions of alpha particles, protons, neutrons, or photons. The overall net conversion of 4 protons to an alpha particle is derived through the summation of some of these reactions. And here's a figure that shows the relative atomic abundance as a function of atomic mass. And we see that this reaction is actually related to the nuclear processes that occur. There's also a low amount of lithium, beryllium, boron. It lies off this line, and that has to do with some of the lack of nuclear stability compared to these elements. We've shown how elements can be formed up to iron. They get primarily through fusion reactions driven by the binding energy increase. Once we try to get above iron, however, we can no longer use fusion, and one of the processes that we rely upon is neutron capture. Very simple reaction, which for synthesis is called the S process, for the slow process. Slow being the number of neutrons. And this is responsible for the formation of elements of A greater than 60. That's an example. Imagine that we have zinc, stable zinc, 68 captures a neutron, goes to zinc 69. The zinc 69 undergoes beta decay. That extra neutron is converted into a proton. We make gallium 69. And as you can imagine, we can build our way up through the chart of the nuclides, hitting a great deal of the stable isotopes along this path. Through extension, we can go all the way up to bismuth through this method. However, from this figure, you can see that there are certain isotopes that we're not hitting. We're not hitting these isotopes here, these heavier stable isotopes, or these isotopes here, the lighter stable isotopes. And as foreshadowing, we'll see that these heavier stable isotopes are made with something called the R process. The R process is when we have neutron captures on time scales that are less than the beta decay. So previously on the S process, it was slow. After capture of a neutron, the isotope had enough time to decay through beta. Well, in the R process, the capture of the neutron is so rapid that the isotope does not have enough time to decay by beta emission if it's radioactive. This occurs when we have neutron densities on the order of 10 to the 28th per meter cubed. You can compare that to, say, how much water there is in a cubic meter of water. This is an extremely high neutron flux, and you get capture times that are in the order of fractions of seconds. And this can produce unstable, neutron-rich nuclei. So imagine that you're sitting out here at bismuth 209, and you have a capture of neutrons all the way out to maybe bismuth 238, and then you get conversion of those excess neutrons to protons through beta decay, and you wind up at uranium 238. So you wind up forming stable or long-lived neutron-rich nuclei, and that's responsible for these nucleons living at this part of the chart of the nuclides and the actinides. This high neutron flux occurs during nova processes in stars. The formation of proton-rich nuclei or neutron-deficient nuclei occurs through this P process, where we have a proton capture process, or we can have photonuclear processes at high Z, let's say of around 40. These photonuclear processes, as we discussed earlier, can result in emission of protons, alphas, or neutrons. As an example, platinum and terbium are from the P process. In the literature, there are various descriptions of the P process, and a lot of that indicates that exploration of the P process is still ongoing. But they're fundamentally, the fundamental aspect of these processes is that they're responsible for the light stable isotopes being formed. A final process that occurs to complete the formation of the proton-rich nuclei is something called the RP process, and this is for rapid proton capture. This occurs with relatively light elements from Z of 7 to 26. You get proton gamma reactions and subsequent positron decay that populate these proton-rich nuclei. This is initiated as a side chain of the CNO cycle, for instance with sodium and neon isotopes. Okay, these two lectures cover topics related to energetics, notations, Q values, understanding different types of reactions were discussed. including reactions with particles such as photonuclear reactions. There was a discussion on cross-section, and these were explored with routes to reactions in nucleosynthesis and the different types of reactions that occur in the formation of elements. Questions that you would be responsible for include such as description of the types of reactions that can occur with heavy ions, notations, understanding of threshold energies, the different type of processes for nuclear synthesis, and some interesting facts about the formation of carbon-12 in nuclear processes that occur in stars. Please respond to the PDF quiz, and after the review of the second lecture, please comment on that lecture in the blog.